Okay, thank you, Yannick, and thank you to everyone who is here attending. I have to say it's really a pleasure to be part of this thematic program at ESI, and that I'm thankful to the organizers for giving me the opportunity to talk here. What I'm going to talk about is this work in collaboration with Xavier Pekar, who gave a really nice talk on the second week of this workshop, Nicolas Boulanger, and my former PhD advisor, Andrea Campoleoni. And this is based on a series of papers that I tried to summarize using this title, from conformal Carrollian scalars to flat space higher spin holography. Higher spin gravity, sorry, I shouldn't say holography because we don't have a holographic correspondence yet, but I will come to this. And my main motivation here will be to try to derive a form of holographic correspondence, but top-down. So instead of trying to ask what could be the holographic dual of a particular gravitational theory in flat space, like gravity or certain compactification of string theory, I will start from the simplest Carrollian conformal field theory that I know of, which is the Carrollian scalar, and try to make a guess, an educated guess, on what could be its holographic dual in the bulk of Minkowski spacetime. So this is the path that I want to follow in this presentation, which is not the path that we took historically, because you will soon realize that when I talk about a putative holographic dual, I have something very particular in mind, which is higher spin gravity in flat space. So don't worry, I will define all these terms. And when people think about holographic correspondence in flat space with a gravity in the bulk and a certain Carrollian conformal field theory on the boundary, maybe higher spin gravity is not the first thing that comes to mind, because it's not pure gravity, it's a gravity with an infinite number of higher spin fields. But I will try to argue that it's a perfect candidate to study flat space holography because the boundary theory is particularly simple. So let me write actually the model that I want to consider here. So if you start from your favorite two-dimensional free scalar, which I'm going to take as a complex free scalar in Hamiltonian form. Okay, so this is the action of a free scalar in Hamiltonian form. I introduce a Lagrange multiplier. Here I should write the determinant of the two-sphere metric. We all know that there are two limits that you can take. The first one is the so-called magnetic, where you just take C to 0 in this action. Can you see here? Maybe. This is the so-called magnetic action. The other one you obtain by rescaling the fields. You send phi to C times phi, pi to 1 over C times itself, such that the symplectic structure is preserved. And you land on this theory. And well, you know that if you solve for the Lagrange multiplier phi, or the conjugate momentum, you recover a more well-known form of this electric action, which is this one, formulated only in terms of a single field, phi star du squared phi. Okay, so these are two possible limits of a free relativistic scalar. Here I'm using the geometry, which is R cross SD. In the relativistic case, it's a perfectly well-defined Lorentzian manifold. Sorry, S2. In the Carrollian limit, this guy contracts to still R cross S2, but this is a Carrollian manifold isomorphic to Scry. I'm really bad at drawing Scry, sorry. Okay. This is the setup, and what I'm going to do in the following is to argue that this very simple theory that we coined as a simpleton in analogy with the term singleton, which is used in the higher spin literature, this very simple theory is actually capable of encompassing higher spin symmetry on the boundary, which is global, and according to the usual ADS-CFT dictionary that we want to, let's say, apply to flat space or try to see if the flat space version could work, it should give us a gauge algebra in the bulk for higher spin gravity. So let me make an important disclaimer before I start, which is that in this talk, there will be no attempt at building a flat holographic dictionary or a Carrollian holographic dictionary. I'm just going to take some results that I know that work in ADS-CFT, take their flat or Carrollian contraction, and make, let's say, an educated guess for a holographic dual. So this is not the complete story, which is very much an ongoing story. And of course, criticisms or comments are very welcome along the way. What I will do here is mostly based on symmetry. So this is a free theory. This remains a free theory in the Carrollian limit. As a free theory, it enjoys an infinite dimensional set of symmetries that I will argue are higher spin symmetries from the point of view of the bulk. And why is this an interesting model? Well, in my opinion, it's interesting because in our attempts to build flat holographic correspondence, we are still missing a form of microscopic description of the boundary theory. So in the case of celestial, we don't really know what the celestial CFT is, although there are many works trying to characterize what should be the celestial CFT. In the Carrollian setting, we don't usually consider particular Carrollian models to try to derive a correspondence because we understand them, I think, still a bit poorly. I mean, the scalar field is pretty much under control, but the Carrollian fermions, for instance, is not completely understood in my understanding. So if this program that I'm going to present is successful, it would be the first microscopic description of a Carrollian CFT dual to a gravitational theory in the bulk, which I think is interesting. And also, it's interesting because it's not any particular gravitational theory in the bulk. It's a theory which is supposed to be UV complete. Right? Higher spin gravity enjoys a huge gauge symmetry. And when you try to renormalize this theory to go to the UV regime, it is believed that the higher spin symmetry is so huge and so constraining that it will prescribe the form of the counterterms that you can write in your action. Of course, this is still a statement to be checked, but let's say you can think of it as a toy model of string theory where the higher excitation of the strings play a role of a regulator like this. Yes, so in this talk, I will only talk about 2+1 boundary dimensions, so 4D, 3D holography. What I'm going to say also applies to higher dimensions. In the case of 3D, 2D boundary, because 2D boundary, 3D bulk, I know there will be maybe some questions. So I think this deserves a separate story. So what I'm going to say is 4D bulk or higher. A lot of what I'm going to say still applies in the case of 3D, but instead of saying this applies, this doesn't apply, I think it's better to have a discussion. Yes. This is precisely what I'm going to do. Yeah, so since you mentioned it, the Klebanov-Polyakov-Sezgin-Sundel model is not a single scalar field, but an ON collection of scalar fields, where n is a large number which controls, let's say, perturbation theory in the bulk. So you have an ON model, you take n large, the G Newton in the bulk is proportional to 1 over n. This is the main result of their construction. But from the point of view of symmetries, higher spin symmetries, for all intents and purposes, you can just focus on one scalar field and it's going to tell you a lot. So the philosophy that I want to apply here is to say, okay, let's start from the ADS-CFT dictionary that I know, meaning that if you have a theory on the boundary, its global symmetries become gauged in the bulk. This, of course, is a statement that has not been proven in any form of Carrollian CFT, but I want to use this philosophy to try to make a prediction in the bulk of what this theory should be the dual of. Okay, I'm not sure I got your question. Okay, so indeed, if you are in a 2D boundary, 1+1, you have potentially more symmetries on your boundary. You can also try to play a bit and have a one-parameter deformation of this theory. This is the theory of that was presented in paper of Glenn, Andres, Komberov, and okay, I'm sorry, I don't remember the third name, where they have precisely these two theories that emerge as the flat contraction of Liouville theory in 2D. But they also have an exponential term which describes the self-coupling of this field phi, and which accounts for the central charge in the BMS-free charge algebra. Yeah, so in 3D, you have more freedom. This setup still applies and will give you a higher spin symmetry. But yeah. Thank you. Okay, so if there are no questions on this setup, then let me start. So, okay, we have these two theories that emerge as the C going to 0 limit of a free scalar. For the discussion that I'm going to do, let me call this phi dagger K phi, where phi is a vector composed of the field phi and pi. And K is a kinetic operator that takes this form. So you have 0 here, you have minus du plus du, and this nabla squared operator. I'm going to define a few things here. So, for instance, if you require conformal symmetry on these models, this will prescribe the scaling dimension of the field. So phi will have a scaling dimension of 1/2, pi of 3/2. So in the language of Carrollian weights, this would be 1/4, 1/4, 3/4, 3/4. I'm going also to, let's say, unify my language. Let me call this K, or Ke for electric. This is Km, magnetic. This is also a K. R for relativistic. And what I want to do now is I want to study symmetries of this action, of these actions. And what I mean by a symmetry, I allow myself to have more general symmetry than just, let's say, the differential realization of conformal transformations or Carrollian conformal transformation. I allow for differential operators acting on my field, which transform like this. So the I is conventional. D is a differential operator now. And I want to say that D is a symmetry of the action S, which I can write in general like this. So d 2x dt square root gamma phi dagger k phi. I just plug this transformation inside of my action. I get delta S is minus I phi dagger d dagger k phi plus I phi dagger k d phi. So in other words, if this operator D satisfies D dagger K is equal to K D, this is a symmetry. And I will also restrict to symmetries that are non-trivial. Yeah. Yes. Yes. So a non-trivial symmetry is such a symmetry such that D is not the composition of another operator with the kinetic operator. You can see that if you have such a symmetry, you plug this inside, it trivially satisfies. In fact, it annihilates, it's zero on shell, right? It's zero if you evaluate on the equation of the phi, which satisfies the equation of motion. It's zero, yes. I want to impose that this is zero. This is the game that we want to play, both for the relativistic action and for the Carrollian actions. In the case of the relativistic action, this was done by Eastwood in 2002 for let's say, for K relativistic. This has been done by Eastwood. So you recover a few things. If D is just a constant, this of course satisfies this property. It corresponds to a phase shift, the linearization of a global U1 transformation. So this is a symmetry. Another possible symmetry is the conformal group. So you get A mu partial mu plus omega mu nu x nu partial mu plus dilations this is the realization of the conformal algebra. This factor of 1/2 here, this linear factor, is because we are acting on a field which has a certain weight. This is the action on phi, for instance. And this generates, of course, SO32. And then you can start to look at higher order differential operators. So let me do a table. Yes. Yeah. That's true. You can introduce a dynamical exponent. Yeah. Yes. Yes. I take the unit sphere. Very good. Yes. So this differential operator here is not just the Laplacian on the sphere. It's the Laplacian on the two sphere minus 1/4. And this 1/4 contains the Ricci scalar. Sorry, I'm a bit sloppy with details. So this is the result of Eastwood that he derived it for the conformal boundary of ADS, so the usual Minkowski space with conformal symmetry. So here I have differential operator of a certain order, and here I have some generators. So at order 0, we have this alpha, which generates a U1 global transformation. We not have enough space. So let me forget about U1. Let me go directly to order 1. You have the conformal algebra, which forms this antisymmetric or adjoint representation of SO3, 2. And I think the main result of Eastwood is that if you go to higher orders, in fact, you generate symmetries which are products of this type of generators. Right? So there are certain symmetrized and with an appropriate projection, symmetrized products of these differential operators. There is no new thing that appears. So for instance, for differential operators of order 2, two derivatives, you get this representation of the conformal algebra. Right, so this would contain, let's say, higher translations, two partial derivatives, product of a translation with Lorentz transformation, product of translation with dilations, etc. So of course, if you go to the bulk, you have to make so this is boundary. You have to make a branching. So if you branch from SO3, 2 to SO3, 1, which is the Lorentz algebra in the bulk, you recover Lorentz transformation and transvections. Here you have to use a branching rule, so you get again this window diagram, and you get also additional things. Okay, and for a differential operator of order S, this generalizes, you get this type of Young symmetry, which branches into this sum. Okay. So what is this mess? Because now we have to make, let's say, a holographic statement. So we want to understand these generators of symmetries from the point of view of the bulk. Yannick. This one. Yes, but I'm keeping it for surprise. So I can give you already the answer because I teased it in the introduction. These symmetry generators will be rigid symmetries of higher spin theory in the bulk. So you can understand, let's say, these generators, the first line, as being the global isometries of a graviton in the bulk. So you take your Firth-Pauli equation of motion, you impose that h mu nu is 0, you look for linearized diffeomorphism that respect this condition, and you will land on the ADS isometry algebra. You can do the same for a higher spin field. What is a higher spin field? It's a field phi with, let's say, many indices that are symmetrized and whose equation of motion, which is of the form, again, box phi plus other terms, equals 0. This equation of motion enjoys a gauge symmetry of the form of this form, where the parameter psi is traceless. So you see that this, if you take S equal to 2, this is just the Firth-Pauli equations of motion, and it's invariant under linearized diffeomorphisms. For higher spin, it's a so-called Fronsdal field, which is a generalization of Firth-Pauli. This is generalization of Firth-Pauli equations of motion. This is generalization of linearized diffeomorphisms. And these fields are very well studied in the higher spin literature. In fact, the higher spin theory in ADS of Vassiliev and collaborators is built using this theory. So, yes. Exactly, yes. Rigid diffeomorphism. So the claim, which I'm not going to prove, is that if you look for the solution of this equation in ADS, this has, okay, you can solve this by going to ambient space. You embed 4-dimensional ADS into a 5-dimensional flat space, and ADS is a hyperboloid in this flat space. You can solve this equation really easily, and you realize that the solutions are given in terms of 1, S minus 2, etc. S minus 1. So there is a precise matching between the spectrum of rigid isometries of the higher spin theory with the global symmetries of the free scalar field. This, of course, is a statement which is only based on symmetries and which cannot, let's say, give you a precise insight about the holographic correspondence. There are, of course, more statements supporting this theory, this duality in ADS. There is, of course, the Klebanov-Polyakov result. There is, even earlier than this, the Flatov-Ronsdal theorem, which tells you that the tensor product of the free scalar representation of the conformal algebra decomposes into an infinite sum of higher spin fields from the point of view of the bulk. So all of this is, let's say, suggesting that there exists a form of higher spin holography in ADS CFT, which is by now well studied. And what we want to do is the same, but in the case of flat space theory and Carrollian boundary. Of course, there are a lot of obstacles in doing this because the bulk theory, let's say the flat limit of Vassiliev theory, is not defined. In fact, it's conjectured to not exist. But I will show you that there are ways to circumvent this no-go theorem. Yes. So this table, here I'm just doing a branching. So I take Young diagrams and I branch them in one dimension less. And this usually decomposes into a sum of all these things are irreducible representation of the conformal group. And I can write them, I can decompose them into irreducible representation of the Lorentz group that sits inside. This is just a branching. This is not a holographic statement for the moment. Okay, so this was the case for ADS. Now let me move to the case of the ultra-relativity scalar. And I will start with the electric one. So as a reminder, the electric theory is just d2x, du, square root gamma, phi star, du squared of phi. Why? Because it's the simplest of the two. And you can play the same game that Eastwood did, but now the kinetic operator is just du squared. And what to find is that the most general solution is given in terms of, well, more stuff. I'm going to define. Okay, so in this expression, L plus minus 1 and K plus minus 1, they are Hermitian differential operator on the two spheres. For instance, you have arbitrary vector fields on the two spheres, arbitrary functions, all arbitrary Hermitian differential operators. And H minus 1 is I partial U. H0 is I U partial U minus a half. And H plus 1 is I U squared du minus U. So you can infer several things from this expression. The first is that the U dependence and the angular dependence is factorized, right? You can have at most differential operators that are linear in partial U. And this is because I impose that my symmetry is non-trivial, so anything proportional to partial U squared is factorized. You can see that at every order, if you decompose this L plus minus 1, K plus minus 1 in terms of angular derivatives, at each order there is an infinite amount of differential operators that are symmetries. And this is usual to what happens in the paper of Duval, Gibbon, Sorvati, where they saw that the rigid symmetries of a conformal Carrollian manifold is infinite dimensional, it's isomorphic to BMS. Yes. I'm classifying symmetries from a purely intrinsic point of view, but you can also classify them using ambient space, and this gives an interesting result because this infinite dimensional, well, of course it's infinite dimensional because it's higher spin, but this, let's say this infinite dimensionality of the differential operators that appear here reduces to a finite dimensional algebra, which is precisely, which contains Poincaré, and which gives you rigid symmetries of higher spin fields in bulk Minkowski. So one of my main motivations now will be to say, okay, what is this symmetry algebra? And how can we reduce it from an asymptotic symmetry algebra to a rigid symmetry algebra in bulk Minkowski? And this is one way of doing it. No, we have. These things are Hermitian differential operators, so they can contain an arbitrary number of derivatives. No, not in U, precisely. Yeah. Exactly. These three possibilities, actually, they close on the SL2R algebra. So we understand them as the conformal isometries of the real line spanned by U. So here you have translation, dilation, and special conformal transformations. Nick, I need your help. Yes, the top one. Thank you. Okay, so now I will. So this symmetry algebra, of course, is huge. It contains higher spin generators, BMS generators, higher spin generalization of BMS generators. What we want to do is to identify a couple of interesting subalgebra that are going to be useful in the bulk. So as an example, for instance, if you take L minus 1 to be just a function, no derivative, and all the rest is 0, this generates large U1 transformation. So this is the sign that you have already a form of electromagnetic theory in the putative dual, in the bulk, whose asymptotic symmetries are large U1 transformation, which are usual if you impose the right boundary condition in Maxwell theory. Okay, let me mention a couple of interesting subalgebra. So if you take K minus 1 to be an arbitrary function of the angles, L minus 1 to be this differential operator, which is just a vector, and L plus 1 to be this, then you would generate the generalized BMS algebra. Right? So you have super translations here. Y is an arbitrary vector, so it generates generalized BMS. You can also add something here, plus W. Then you would generate the Weil BMS algebra. So these generators, the form of these differential operators is matching with the pullback of to Scry of a Weil BMS transformation. There is also a funny extra generator, which corresponds to the H plus 1 here. So if you have this Z of X times H plus 1, these are extra transformations that we haven't seen really anywhere, but which have a non-zero commutation relation with super translation. So that's a bit funny. Exactly. Yeah. Mm. And the commutator of this extra transformation with a super translation gives back a vile, but with a function which is given by the product of a super translation and is z. Yeah, exactly. So this is a subalgebra. If you include also this generator, you land on the generalization of vile BMS. You can't have only this and not the W. Yeah. Okay. Let me now do it for the magnetic case. Yes. Yes. No. Right. Yeah. 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 That's true. No, we didn't have a look at this. Yeah, I'm not sure what they would, these generators, what they would correspond to in the bulk. Because I agree that on the Carrollian boundary you can have a certain degree of non-locality. In the bulk, it's a well. So you can also justify a form of non-locality in the bulk. Yeah, that's true. We are also going to land on a higher spin algebra, which is not W1 plus infinity. Yeah, yes, you're right. I'm restricting to local differential operators. So the magnetic case is a bit more involved because the theory is more complicated. But what's remarkable is that if you classify all these symmetries, you land precisely on the same algebra, parameterized in terms of the same generators, and they close on this an algebra which is isomorphic to this one. Yes. Well, so this, if I restrict to local differential operators, I think this is the biggest one that you can have. Sorry? Yeah. Not really. This extra generator H+1, no, they correspond to special conformal transformations of the real line that they don't really have an interpretation in the bulk. Of course, we can view them as inversion, translation, inversion, so they should be a form of translation at infinity. But we haven't made this statement very clear for the moment. Well, this appears in the case of the scalar field. What I'm going to show now is that not all of these symmetries have to be gauged in the bulk. You should gauge a subset of these symmetries which correspond to true symmetries of your Poincaré vacuum or your higher spin vacuum. So yes, the case of the magnetic, I will not do it now in the blackboard. I just want to say that they generate the same isometry algebra. And this actually comes from the fact that the magnetic and electric theories are equivalent up to a non-local inversion. So if you remember the magnetic theory, kinetic term, X conjugate, plus phi Laplacian squared times phi. And okay, Xavier already mentioned this in his talk 2 weeks ago, but if you are able to invert this differential operator, this shifted Laplacian, then you can solve for phi through its own equation of motion and recover something which has two derivatives in retarded time. So it's precisely the magnetic theory. And when are you able to invert this Laplacian? Well, you can have a look at the action of this on an angular, spherical harmonic, L, and you will find something like minus L plus 1/2 squared YL. So this, let's say, this is always invertible on the space of spherical harmonics. So the two theories are equivalent, and so of course it's not a surprise that their isometry algebras are also equivalent. Actually, let me. No, I want to keep this. So, so okay, now we obtain an algebra which is infinite dimensional at every order, which one could try to argue that it's an asymptotic symmetry algebra in the same way that GBMS is an asymptotic symmetry algebra or Weil BMS. But the question now is how to select an algebra inside of this big infinite dimensional algebra, which represents higher spin symmetries, higher spin isometries of a particular theory. So, okay, one possible attempt is to take a Fronsdal field in Minkowski. So it satisfies also an equation of motion of this form, which is invariant under transformations. And you look for solutions to this equation. Where psi is traceless. And you will find exactly the same type of generators as in ADS. Yes. No. This is a purely classical statement. I'm going to comment also a bit in the end about why one of them should be better behave for holography than the other. But I think it's still important that they're classically equivalent. It means that you can move from one to the other. I mean, you can only use one of them to define your boundary theory, then the other one would be classically equivalent. So if you solve this equation, this is actually much easier if you do it in flat space rather than in ADS. You will find that parameterized in terms of okay, if you use Cartesian coordinates, let's say, you're going from 0 to s-1. So you recover precisely the same set of reducibility parameters that we found in ADS. So they are two-row Young diagrams with s-1 in the first row and t in the second one. So what we want to demand is that there exists a subalgebra inside of this generalized algebra of symmetries that contain this spectrum of generators. So there are a couple of ways to do this. The first one is to, yes. You mean the H+1, the special conformal? The other one should correspond to pure large gauge transformations, like super translations correspond to asymptotic symmetry. Pure super translations correspond to symmetries which are only asymptotic. Yes, here the route that I want to follow is to find a subalgebra of rigid symmetries. Precisely, it's the symmetries of vacuum. If you put phi equals 0, this is a solution of the equation of motion, and these are the isometries that preserve this condition. Of course, if you were to make a go to boundary gauge, make a 1/r expansion of your field, you can ask what are the large transformations, and this has been done in a paper by Andrea, Dario Francia, Carlo Heisenberg for the case of the Fronsdal field. And they found a set of asymptotic symmetry generators for Fronsdal fields, which is part of our big algebra. So everything checked out. Okay, great. So okay, how to select a rigid subalgebra? you can try to impose several things. You can impose some conformal killing equations, like you do to go from super rotations to Lorentz transformations. You can use ambient space techniques, as was mentioned earlier, or you can simply go to the bulk, which is what I'm doing now. I identify a spectrum of generators, and I try to see if there is something that fits inside. And now let me move to this very much awaited blackboard. So here is how it works. If you start from your ADS4 algebra of symmetries, which is SO3, 2, there is a way to construct the higher spin algebra of Eastwood, which is canonical. So you start from your algebra of symmetries, you take the universal enveloping algebra. So you introduce, let's say, an associative product on this algebra. You take many products of your generators of conformal isometries, and you can find a unique quotient which reproduces this algebra. And the quotient corresponds precisely to these generators that are zero when evaluated on the boundary field. So this boundary field, which is the singleton in the higher spin literature, defines a bulk field, which is just an extension. And when you evaluate the universal enveloping algebra of conformal isometries on the symmetry, on the equations of motion of this bulk field, you land on HS4. Now, let me show you how this works in a Carrollian context. So you start from your Poincaré algebra, you take the universal enveloping, and you have to find a quotient that reproduces a certain higher spin algebra. And what we found in a paper with Andrea is that there is a unique way of doing this, and we land on this algebra IHS4, which is the lambda going to zero contraction of the ADS1. Now, if you start from the boundary, let's say you take the C going to zero limit, you have two possible ways, but they are equivalent. The symmetries of these theories, they form a sort of asymptotic higher spin algebra in which fits this IHS4 algebra. And you can do even better. You can start from the universal enveloping algebra of Poincaré, evaluate it on the bulk field defined by these theories, and you will also land on IHS4. So now the main actor of the game is IHS4. You have to understand what is the dynamics associated with gauging this algebra. It's unique, so it's the unique one that you can build from a universal enveloping algebra construction. And well, also it's canonically defined by this arrow, let's say. If you take the flat limit of a singleton, as Xavier explained in his talk, you land on a certain bulk field. And if you evaluate all the possible symmetries, higher symmetries on the equations of motion of this bulk field, you will land here. I'm not saying that there are not other ways of defining higher spin algebras, but if you want to do a carbon of what's happening in ADS, I think this is the only way. This is unique. Okay, so now in the 10 minutes that I have left, I will try to argue why this IHS4 is a good candidate for higher spin holography in flat space. So IHS4. So if you look at the possible generators of IHS4, they have, of course, this form for T 0 and S minus 1 and S greater than 1. So spin 0 is not really included in our setup because it's not a gauge field. It doesn't have any form of gauge symmetries. But from spin 1, these are the rigid higher spin generators of higher spin symmetry. And you can try to say, okay, let me take this algebra, IHS4, with its structure constants, and let me gauge it. So what I mean by gauging is you introduce a potential, which is a one form, taking values in this algebra. So there is a sum, omega, I'm not going to write all the indices, B, M, A, B. I can compute its curvature, F, A plus AA. And I want to see if there exists some equations of motion that I can impose on the curvatures, such that I propagate a free spin S field. Why free? Because this algebra is horribly complicated. So first I want to study the linearized setting to make sure that I'm indeed propagating the correct number of degree of freedom. So I'm not going to do the detail, obviously, but this is the object of this paper with Nicolas Boulanger, Andrea Campoleoni, and myself from 2023, where we show that there is a way which is precisely similar to the one that happens in ADS, such that the equations of motions on these curvatures, so it means that you decompose this curvature in terms of these generators M, you set some curvatures to 0, you set the trace of the last curvature to be 0, which means that there is a form of higher spin Weil tensor that propagates degrees of freedom, and you realize that you are propagating spin S fields, free spin S fields, for all S greater or equal to 2. The case of electromagnetism is a bit special, but that's also the case in ADS. Yes? No. That's the problem. I mean, there exists an action for free higher spin fields in Minkowski space and in ADS too. But now I'm going to say something which is, well, I think important and also my conclusion, which is that the usual starting point for higher spin fields in Minkowski spacetime is the Fronsdal field and the Fronsdal action. What we found in this work with Nicolas and Andrea is that actually what comes out naturally of the equations of motion is not the Fronsdal field, but is something else, which is related to a curvature with mixed symmetry. Okay, you can reconstruct a Fronsdal field from the equations of motion, but it is a non-local operation. These are the main takeaways of this paper, is that the Fronsdal field is not fundamental. Which come a bit as a surprise because everybody starts with the Fronsdal field. But okay, what we are trying to argue is that if you want to have a version of flat space higher spin holography, you should start considering also other fields, which are usually connections in the higher spin literature. Okay, so now let me conclude. So our approach is to try to go from the simplest Carrollian field theory to the bulk, and using a gauging procedure, try to produce equations of motion for an interacting theory of higher spin gravity. These are only, of course, preliminary steps, but which suggest that the higher spin ADS-CFT correspondence also has a flat space counterpart, and which is in all regards smooth. Of course, the story in flat space is very much different than in ADS. We know that. Also in the case of gravity. For instance, one thing that you may say is that, oh, but your boundary theory, the simpleton, may be too simple. Because if you look at the stress tensor, T mu nu for the simpleton, and in particular for the electric theory, you find that it has schematically this form. So there is a scalar here, 0 here, you have a vector here, and you have -1/2. The stress tensor for the electric theory takes this form. The magnetic theory is different. So yes, that's also tied to Romain's question, whether they are still equivalent. I think it shows that even though they are equivalent as classical theories, there are many features which are not equivalent between them. So the stress tensor takes this form, and you might say, okay, well, this M, for instance, is a U independent, and this N is linear in U. So of course, you are never going to be able, if this is truly the stress tensor of let's say the spin 2 counterpart of a bulk graviton, this will never be able to accommodate for radiation. But this we already know in the case of flat space holography for gravity, as you showed in your paper, that you need to introduce sources in order to be able to account for radiation. And you might also recognize that this stress tensor has precisely the right form to encompass the Bondi mass aspect and angular momentum, the boundary theory. So yes, let me conclude with this statement that a lot of things that were considered to be undoable in flat space concerning higher spin holography may actually have a nice description in terms of this simpleton. There are a lot of things that you still need to do in order to have a full holographic description, but along the way, we hope to understand a lot of things also related to flat space holography in general. So thank you for your attention. So okay, when you gauge this IHS4 algebra, you realize that some curvatures are of this form. So some of the curvatures, in particular, let's focus on spin 3 for an instant. So you have 3 curvatures. You have FAB symmetrized, FABC, which is of mixed symmetry, and FABCD, which has a window shape. This is the form of the curvature in this case. So you see that if you impose F is equal to 0, you can use gauge invariance to set E to 0. So E is no longer the Fonsdal field. It doesn't propagate anything. On the contrary, it's going to be this curvature which contains the not the radiative, the propagating degrees of freedom. And you can go back from here to another Fonsdal field. By use of the Poincaré lemma, which is something that you can only do in flat space. So this would be the fundamental field that everybody is starting with. This is the Fonsdal field. What we found is that actually this is more fundamental than the Fonsdal field. Okay, that's actually maybe an interesting remark. Mm-hmm. How do I interpret the fact that this is this spin connection? Well, to be fair, I mean, if you try to start from a Fonsdal field, you find the rigid isometries of a Fonsdal field, and you want to build an algebra which satisfies the fact that, for instance, the commutator of translations with the rigid isometries of a Fonsdal field, so spin 2, spin S, gives you what you would expect. You find that no algebra exists. So there was this old, let's say, tension in the literature that you cannot define higher spin algebra in flat space because the action of translations on higher spin generators is ill-defined. This is, I think, one way of solving this tension. You say, don't start with the Fonsdal field. Don't insist on doing that, otherwise you will fail. And start instead with this. No, in 4 dimensions or higher, you have to consider all of them. Yeah. Yes, in fact, yes, thank you. So the bulk description of a simpleton, in fact, actually, both the bulk and the boundary are not unitary theories. So this is because they don't form a unitary reducible representation of the Carroll algebra or Poincaré algebra. I would say that this is not necessarily a killer in the sense that we have to expect a certain degree of non-unitarity from the point of view of the boundary. But one thing which is, I think, really interesting that we would like to understand is how, starting from a non-unitary boundary theory, you arrive at a unitary bulk theory, because Fronsdal, or any propagation of spiness, is unitary. Maybe there is an issue to be solved. Maybe it sits in the radiation. Maybe it sits somewhere else.